Delaware Tech, Chemistry 100, Chemistry 110 with Dr. Marc Taylor, Unit 4, Compounds, Bonds, and Nomenclature. This corresponds to the Timberlake Chemistry textbook, Chapter 6, Ionic and Molecular Compounds. This module will be focusing on valence electrons and Lewis dot structures. We're going to be covering in this unit valence electrons and Lewis dot structures and what that means, specifically the Lewis dot structures of individual atoms. This is how to draw atoms showing the valence electrons around them. We'll talk about cations and anions. Cations are positively charged ions. Anions are negatively charged ions. We'll talk about the octet rule. This is the rule that states that many atoms attempt to achieve having a total of 8 electrons around them, and that is accomplished by either losing electrons, gaining electrons, or sharing electrons. And this can be represented by the Lewis dot structures, both as individual atoms and within compounds. So we'll talk about the nature of ionic compounds and covalent compounds, also known as molecular compounds. We'll also talk about how to name these compounds. The systematic method of naming anything is called nomenclature. So we'll be talking about the nomenclature of ionic compounds, the nomenclature of polyatomic ions, which are a part of many ionic compounds, and then we'll talk about a separate set of rules for the nomenclature of covalent compounds or molecular compounds. Then we'll talk about the concept of electronegativity and bond polarity, and a little bit on VSEPR rules for Chem 100, and we'll go into it in more detail for Chem 110. These are rules that predict the shape of molecules around individual atoms that have other atoms attached to them. And then the last part of this unit will be talking about how the polarity of individual bonds and the shape contributes to the overall polarity within the molecule in terms of positive and negative charges, or partial positive and negative charges, and how this affects the forces between molecules called intermolecular forces. So let's start with valence electrons. Valence electrons have a number of definitions. We're going to keep it simple for these two courses. We're going to say they are only the outermost electrons in the s and p orbitals only. We're going to disregard the d orbital electrons and the f orbital electrons because the rules become extremely complex. So atoms, as you remember, are uncharged particles by definition, so the number of electrons has to be equal to the number of protons. In other words, the atom has the same number of electrons as dictated by the number of protons, which is dictated by the type of element it is. Ions, however, have gained or lost electrons. The protons don't change unless you're in a nuclear reaction, so we're only talking about gaining or losing electrons, so now the number of electrons can be different from the protons, causing it to have a positive or negative charge. Polyatomic ions are groups of ions, usually covalently bound. We're not going to worry about that. But they're groups of atoms that are bound to one another that have an overall charge for that group. And you typically find these within ionic compounds, ironically enough, and then not covalently bound compounds. I know that seems a bit confusing. Now, anions are negatively charged particles, and there are many, many anions. You can see there are single atom anions like fluorine minus, which we call fluoride, chlorine minus, which we call chloride. I'll skip over oxygen minus 2, which we call oxide. Nitrogen minus 3, we call nitride. You'll notice a pattern. They all end in the letters IDE, ide. But we also have some polyatomic anions, ones with more than one kind of ion. Shown here are hydroxide, that's OH minus. CN minus is cyanide, so it keeps the rule, but we have others that end in ite and ate. Shown next, NO3 minus, is nitrate, and the last one in this row is hydrogen phosphate. Cations are positively charged ions. So these are ions that these are derived from atoms that have lost electrons and become positively charged. Hydrogen ion, which is H+, and we just call it hydrogen ion because it's the only positively charged version of hydrogen. Similarly, sodium ion, Na+, and potassium ion, K+, they only form +1 charged ions if they're going to be plus charged, and therefore we just name them by the same name as the atom. So it's hydrogen ion, sodium ion, potassium ion. Magnesium ion, since +2 is the only normal form of that. Calcium ion, aluminum ion, those are all the standard positively charged forms of each of those. However, these other ions that are within this first group, iron +3 and chromium +6, we have to say which number they are because iron can form several different kinds of positively charged ions, and chromium can form many different types. So we would say iron 3 ion. We don't even need to say the plus. We just say iron 3 ion and chromium 6 ion. And then we also have a couple polyatomic positively charged ones. The first one is called hydronium ion. It's derived from water. And the last one is called ammonium ion, and that is derived from ammonia. And that 4 should be a subscript. I'll fix that. Now, we have different kinds of bonds between atoms within a compound. There are going to be 2 major categories. Ionic bonds, which are formed between 2 ions, 2 or more ions, and they have to be oppositely charged to attract. We also have covalent bonds. Instead of having ions formed from atoms where one atom has lost electrons to be positively charged and one has gained electrons to become negatively charged, and then they attract each other, as in an ionic bond or an ionic compound. Covalent bonds are formed when atoms share their electrons, so there are no formal charges between them, so they share the electrons, and both atoms behave as if they have both of the shared electrons between them. So ionic compounds are composed of ions that are positively and negatively charged, so that makes sense. Ionic compounds from ionic bonds that are formed between ions. Molecular compounds, also known as covalent compounds, are formed with atoms that are bound by covalent bonds. Electronegativity, which we'll talk about a bit later, is the attraction of an atom within a bond. So if you have one atom attached to another atom, each atom has a certain strength that it draws the shared electrons towards it, and the greater the strength, the greater the electronegativity. So electronegativity means how much it pulls those negative electrons towards it when it's sharing it with another atom. And then we have intermolecular forces. Inter means between, intra means within. So the ionic bonds and covalent bonds are called intramolecular bonds because they are within a compound. But when they're between compounds, between molecules, we call them intermolecular forces. And they're much, much weaker than the ionic and covalent intramolecular bonds because they're not full bonds. And as a result, they're much, much weaker, but there are many of them, and they add up and become very important. And we'll talk about that in the last module of this unit. So let's talk about valence electrons, Lewis structures, and the octet rule. So valence electrons, as I mentioned, are the outermost S&P orbital electrons. They're the highest energy electrons in the atom, and these are the electrons that are really responsible for the chemical properties of that atom, how they behave, their chemical reactivity. And the reason is these are the electrons that other atoms can actually see. The other atoms don't see the inner atoms inner electrons when they interact with an atom. They only see the outside of that atom, and the outside of that atom is predominantly the outermost electrons, and we're only going to discuss the S&P orbital electrons. So what that means is that atoms of the same group, that's the same one column within the periodic table, they actually have the same number of valence electrons because they have the same number of S&P if you look vertically down a column. For instance, if you look down the first group, which is group 1 or 1A, you have hydrogen, lithium, sodium, potassium. They all have only one s orbital electron and no p orbital electrons for that outermost set. and therefore they have one valence electron each. Everyone in that column does. And that is true for every column in the periodic table. If you find an element, all the elements below it have exactly the same number of valence electrons. And I'm abbreviating that as VE with a negative sign here. So this is the reason why that atoms within a group, within a column in the periodic table, they not only have the same number of valence electrons, but they have many similar properties and similar chemical reactivities. Now, atoms on the periodic table, the goal for many of them is to get electron configurations that look just like noble gas configurations. Noble gas electron configurations, we learned in the last unit, are configurations where all the electrons for that row of the periodic table are filled. All the orbitals are filled with electrons. So, for instance, neon, that row has a full set of 8 electrons, and the goal is to fill those electrons to get to the noble gas neon's electron configuration. And all atoms tend to want to do this. There are many exceptions. We're not going to talk too much about those in this course, but in general they want to get to 8 electrons. And the way to do that is to either add enough electrons to add up to 8 electrons, or lose all of their electrons in that row so that they have no electrons in that row, and the row before it has 8 electrons. So it's kind of the same thing. So if somebody says 0 valence electrons, it really means 8 in the previous row, but we never say that out loud. And then the third way to do this, and by the way, the first 2 ways, losing and gaining electrons, will produce ions. And you find that in ionic compounds. But there's another way for atoms to get their 8 electrons, especially if 2 atoms both want to gain electrons. How do they both gain it? Well, they can't both gain it, so what they do is they share electrons. And sharing electrons allows them to think, and I'm going to use the word think in an anthropomorphic way here, both atoms think they have 8 electrons. And I'll show you examples later so that what I just said will make a little sense. The fact that they want to achieve 8 electrons in their outer shell of s and p orbitals is called the octet rule. Octet meaning 8, a group of 8. There are exceptions. If you're in the first row, hydrogen and helium, or if you're trying to get to the first row by losing electrons, like lithium, which is number 3, it can lose 1 electron and have its electron configuration just like helium. Well, we would call that the duet rule, and that's not a real name. It's a name I made up, thought I was clever about it, and found out that every other chemistry teacher on the planet came up with the same fake name for the rule for the first row of the periodic table, the first period. So we'll just jokingly call it the duet rule, but everybody knows what that means. The other big exception are all the transition and intertransition metals. They have crazy complex rules based on a whole field of study called crystal field theory. We're not going to talk about that. We barely even touch that in Chemistry 151, which is several courses more advanced than this one. And we've talked about valence electrons, or the outermost electrons. Well, all the inner electrons are called the core electrons. These are the ones that other atoms don't really notice. They're not really exposed to. They don't interact with. They're just there. So if we look at the periodic table, and I've got this unmarked periodic table, and I'm not sure what that gray box, I know what that gray box is, but if we look at how many valence electrons there are, we can just count from left to right, only looking at the group A elements. Remember, we're going to focus on group A, we're going to ignore the transition for just a moment, and only count from left to right, because remember, these were named 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and now we call them 1, 2, 13, 14, 15, 16, 17, 18. You can use either name. Both are used quite frequently. On tests, I'll give you both names if I give you a name at all. And so the number of valence electron is determined merely by counting up how many s and p electrons total. Remember, you can have a maximum of 2 s orbital electrons, and you can have a maximum of 6 p orbital electrons. We learned that from electron configurations. Well, 2 plus 6 is 8, and the goal is to get a configuration that looks like the noble gases, which are that far right column underneath the number 8. So most atoms in the A groups want to have configurations like noble gases on the far right, and they do that either by losing enough electrons to go backwards to that row or gaining enough electrons to go forward. So what this means is everything under group 1 is 1 valence electron. Everything under group 2 is 2 valence electrons. Everything under group 3A is 3, 4A is 4, 5A is 5, 6A is 6, 7A is 7, and 8A is 8. So what do we do about all the elements in between? Well, they have their first 2 electrons from their s orbital, and they don't have any p orbital electrons for that row. Whatever row they happen to be in, they haven't hit the p orbitals. So every transition metal for your purposes will be counted as 2 valence electrons. Now, I will tell you right now, that's not true. So there are certain other rules where they say, okay, in some cases it's 1, in some cases it's 2, in some cases they count the Ds. That makes it much more confusing. We're just going to say that everything in the transition metal groups are 2 valence electrons. So what that means is if I count from left to right, every column, I have 18 columns here, and I ask how many valence electrons in each of the columns, well, the left side is 1, group 2 would be 2, group 3, now I'm in the B, I'm in the transition metal, I'm not group 3A, I'm in group 3, that's also 2. Group 4 is also 2, 5 is also 2, 6 is also 2, 7, 8, 9, 10, 11, 12 is also 2. It's not until we get to group 13 or 3A that we jump to 3 valence electrons, then 4, 5, 6, 7, 8, finally on the right side. So that's how we count valence electrons. So, do you remember what we just did? Here's a little quiz, and remember, if there's a charge, you have to add or subtract electrons. Fluorine. Well, fluorine, if we go back, fluorine is actually the element right under the number 7. So that's 7 electrons. It has 7 because it has 2 s orbital electrons and 5 p orbital electrons. Oxygen, well, if we go back, oxygen is right underneath the number 6. I hope you have your periodic table out and you're looking. You can see the numbers. You just count from left to right, skipping the transition metals. Helium, well, helium, you'll notice it's sitting right underneath the number 8, but it is actually only number 2. And that is because, remember, helium is pushed over to the 2 column, to the 2A column, because we're talking about where the electrons are right now. So we would move the helium over to 2. That's the only confusing one on this. So I'll let you go through these. If you see a positive charge, you have lost an electron. So if it started with 1 and you have 1 positive charge, you now have 0. So you can freeze the slides right now, or freeze the video right now. Okay, and now I'm going to show you the answers. Fluorine is 7, oxygen is 6, and everything underneath oxygen is also 6. Helium is the oddball, it's 2. Magnesium is 2. Sodium is 1. Potassium would be 1, but it lost an electron, so it goes down to 0. Nitrogen is 5. Neon is 8 because it's all the way over to the right. Iron is a transition metal, so it only has the 2 s orbital electrons and no more. Carbon is 4. It's right in the middle of the 1 through 8 count. Iodine plus, iodine normally would have 7 valence electrons, but it lost 1, so it's only 6. Cobalt is one of the transition metals, so it's still only 2. And boron is in group 3A, or 13, and therefore it has 3. So let's look at another set with more ions in here, and you'll see a little pattern. These are all common ions or non-ions, or either the atoms themselves or that they're found naturally, or the ionic form, the charged form of these ions, of these atoms that are very, very common. Fluorine, it was 7, it bumps up to 8. Oxygen was 6, You add 2 more electrons, it's also 8. Hydrogen is in the first row. It used to have 1 electron, and you add 1 more, it's 2. So you notice everything in the first row wants to get to 2 electrons, like helium. Hydrogen plus loses its only electron that it has, so it's 0. Potassium has 1 valence electron, but potassium plus has 0. Phosphorus minus 3, well, phosphorus has 5, just like nitrogen, but phosphorus has gained 3, so it's 8. Argon is a noble gas. The noble gases are all 8 except for helium. Magnesium used to be 2, if you look over on the left, but you lose 2, so it's 0. Carbon used to be 4, but this is carbon minus 4, so you don't subtract 4, you add 4. It means 4 extra electrons, that's 8. Iodine used to be 7, but we're adding an electron, so it's 8. Calcium is in the alkaline earth metals, and that's 2 valence electrons. Everything under that is 2, but now you've lost 2, so it's 0. And chlorine is a halogen, like fluorine, chlorine, bromine, iodine. It's in the 17th column. We call it 7A, or group 17. We've gained an extra electron, so it is 8. Take a look at this column. All of the numbers are either 0 or 8, except for the ones in the first row. Hydrogen minus, which we call hydride, and helium are 2, because that is the goal, to get 2 or to lose everything. So they either all lose all their electrons or they gain enough to become 8, with the exception of the first row. So in the first row it's either 0 or 2, typically, and in the every other row it's 0 or 8 is the goal. It doesn't always happen, but it is the preferred form for many of these atoms. So as a result, we find that looking at the periodic table, there are various obvious charges that are common within elements in the same group. Remember, in group 1, on the far left of the periodic table here, these are the alkali metals plus hydrogen, and if they lose 1 electron, they become 0 valence electrons, which makes them just like a noble gas. So they tend to be +1 charge. The second column, the alkaline earth metals, so that would be beryllium, magnesium, calcium, etc. They want to lose 2 electrons to go backwards to be like a noble gas. So they tend to form +2. I should have started the other way here. Now looking on the other end, on the far end, the far right side, that last column in kind of a teal color, those are the noble gases. They already have 8 valence electrons. They don't want to do anything. They don't want to gain electrons. They don't want to lose electrons. They stay the same, so they don't want to form anything charged. So they tend to have 0 charge. They tend to be uncharged. Whereas the halogens, which are in this odd pea green color, this sea green, pea green color, that second to last column, the 7A or 17, they're all 1 away from a noble gas. They just need 1 more electron. So they all tend to, the most common form of those is a -1 charge, which gives them 1 extra electron. The pink would be everything underneath oxygen. They tend to want to gain 2 electrons. So they tend to form -2 ions, etc., until you get all the way to carbon, which can gain as many as 4 electrons, forming a -4 charge. And each of these would result in a noble gas configuration with 8 valence electrons, satisfying the octet rule. On the other end, we have the ones that want to lose electrons. So on the left side of the periodic table, they tend to want to lose electrons. On the right side, they tend to want to gain electrons. And on the far right side, they don't want to do anything. They're happy the way they are. So the alkali metals and hydrogen tend to want to lose 1 electron to become a +1. The alkaline earth metals lose 2 to become +2. The group 13 or 3A tend to want to lose 3 electrons. And you come back to carbon, which can actually lose 4 or gain 4 to get to a noble gas configuration. Now, Some of these charges are the only common charges that the atoms form, and some of those are just one of the most common form. There are other possibilities for a lot of them. So don't be confused by that, but we're talking about the most common charges. The more formal name for a charge, even when something doesn't actually form an ion, is called the oxidation state, and we'll talk more about that in Unit 5. So valence electrons in the same group will have the same number of valence electrons. There'll be one column will be all valence, one valence electron, another column will be all 2 valence electrons. So you can easily figure that out by looking at the group number on the periodic table. They're the same as the outer electron configuration. How many S's, how many P's, ignoring the D's and F's. So every element within the same column will have the same last part of its electron configuration. So the periodic table position tells you how many valence electrons and the most common charge. The same number of valence electrons for all the members of the group, the same properties, the same chemical reactivity. Similar, not identical, but very similar. So you end up forming a lot of the same charge types and the behavior. All right, so for example, in group 2 or 2A elements, the beryllium, magnesium, calcium, strontium, barium, radium, these are the ones on the colored periodic table that I gave you that are in orange. Well, they all have 2 valence electrons, and they'd love to lose them. So they all tend to form +2 ions. And in fact, that's the only common ion for all of them. And that satisfies the octet rule because they end up with 0, which behaves as if it's 8 from the previous row. And they're all reactive metals. They all react in very similar ways with other elements. They all form dihalides. In other words, they react with 2 from the halogens. So you might find magnesium chloride has 2 chlorines. Calcium chloride has 2 chlorines. Calcium fluoride has 2 fluorines. Magnesium fluoride has 2 fluorines. They react in the same way with the same ratios. They also all form monooxide compounds. In other words, they react with a single oxygen. Notice that the oxygen likes to form a -2 charge, and the magnesium likes to form a +2 charge. That balances things out. And if you look at the magnesium in the first compound here, magnesium chloride, MgCl2, each chlorine likes to form a -1, and we have 2 of them, so 2 negative charges balances the 2 positive charges of the magnesium itself, and we'll get into this when we start talking about ionic compounds more. So the group A atoms, these are the ones in groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, or groups 1, 2, 13, 14, 15, 16, 17, 18. They want to achieve the octet rule. They can do that by either gaining or losing electrons, and we've talked about that, to form ions. Cations are formed by losing valence electrons and frequently become a total number 0, which is like 8, but we're going to say it's 0. The anions are formed by atoms on the right side of the periodic table trying to gain enough to be like noble gases, so they become negatively charged. And they'll end up with 8 valence electrons most of the time. Not all of the time. There are exceptions to all of these things. The other way, and what I've just described happens in ionic compounds. In covalent compounds, they share the electrons. So each atom that might have 4 or 5 or 6 or 7 or 8 valence electrons to begin with shares it with an atom that doesn't have 8 electrons, so that both of them think they have 8 electrons. Metals don't usually do this. So the left side of the periodic table typically isn't involved in this kind of reaction. It's the right side elements. The non-metals tend to do covalent bonds, and if it's just a non-metal with a non-metal, they both want to form, they want to gain electrons. Well, the only way for both to gain is for them to share. The group B metals are much more complicated. I mentioned this before. They have much more complicated rules, but the group B elements almost exclusively form positively charged ions called cations. So you almost never find a metal that's negatively charged. It might be neutral with no charge because it hasn't reacted yet, or it might have a positive charge, +1, +2, all the way up to even +8. But you rarely find metals that are negatively charged. So let's talk about Lewis structures. Lewis structures are structures that were developed by Gilbert Lewis over 100 years ago. And he wanted to have a way of keeping track of the valence electrons, and it's very simple what he did. It works for both neutral atoms as well as ions. And he merely drew the symbol and then drew dots around the symbol representing all of the valence electrons. And neon has a full set of 8. So we typically write the 4 spread out first, and then we write the other 4 so that you have 4 pairs of electrons around each side of the symbol. So you don't typically pair them up until you have to. If you have 8, you have no choice. They're going to be 4 pairs. So phosphorus has 5 valence electrons. So 4 of them take one side each, and then you put the 5th one paired with another. Chlorine has 7 valence electrons, so we put 4 in there, and then the other 3 have to find a pair. Now you might be asking, well, does it matter which side I pair up? No, it does not. Sometimes it's easier to draw them on one side or another, or it's more convenient when you're drawing more than one atom bound to each other. But technically, it doesn't matter in phosphorus whether that pair was on the top, on the bottom, on the left, or on the right. As long as you show that there's 1 pair and 3 lone electrons, separate electrons, what we call unpaired electrons. Chlorine has 1 unpaired electron, so it has 1 space for another electron. Chloride has gained an extra electron, so instead of 7, it now has a full set of 8. Sodium starts with 1 valence electron, it's over there on the left, and to make a positively charged ion, it loses that. So sodium plus, Na plus, is the Lewis structure for sodium ion. There are no valence electrons. We don't draw any dots on it. Don't draw the 8 from the row before that. That's very improper. So we just write it like this. And so here's a set. You can practice this on your own. Remember, everything in the same column will have the same number of valence electrons. I'll pause it here. You can practice on your own. And then you can check now. I'll just show you the answers to these in a second, but I'm going to show you a few other problems. You can try these. These are ions, common ions of each of these. Some of these have lost electrons, the positively charged ones. Some have gained electrons. I'll stop here for a second. Okay, now I'm going to show you the answers. The first set are right here, and you can see that the atoms are paired. You'll notice in this fake periodic table, they skipped the entire transition metal. So it went right from number 4 to number 5 and from number 12 to number 13 without showing that big space of the transition metals. So don't worry about that. It's just a way of cramming it all in one box. And then the other elements, well, the first 3 are here are metals. They've lost the only valence electrons they have, so there are no electrons. Whereas the last 3 are all non-metals. They've gained enough electrons to each get a set of 8. And that's how it is. And we'll stop here and start on ionic compounds next time.